Hello everyone and welcome to a new episode of data visualization with Svelte and D3. So today is going to be a special episode as we're looking into a more advanced topic, because today we want to have a closer look on a special widget that we had on our spiegel.de website, German news magazine where I'm working, during the conclave in Rome when the new Pope was elected. And as you know, there is this chimney on the Sistine Chapel. Let me just switch to my browser. And the smoke which is coming out of this chimney is signaling whether there has been a new pope elected or not. And it could be black, that would mean there is no pope elected yet. And it could be white, which means there is a new pope, which was the case like in spring 2025. And then we had like this widget that you see here on the website, and we could like use this to put it directly on our landing page to show our readers if there was a successful election of the new pope or not. And yeah, the thing is, we want to not go into the contents or the details of like the election of a pope or whatever. We want to go into the details of the technology behind, because we coded like this widget just from scratch, and we animated this like clouds here from the smoke also from scratch, and we wanted to have that responsive so that it works on smaller screens as well. It looks nice on mobile, it looks nice on desktop, and we also wanted to change the color very easily. So yeah, we didn't want to have a movie because that would be a little bit difficult when it comes to responsiveness. We did want to visualize this directly. And for that, we used WebGL and Svelte. And yeah, I'd say let's go into the code. I have my code editor here, and I have a local version of our little application here on the right hand side. You can see it's running on localhost, and also now there's black smoke and not white smoke anymore, because the standard setting in this widget is that there's black smoke, because you have far more often black smoke than white smoke. All right, so let's have a look how this application is build up, how the setup does look like. So you can see here, this is a like standard Svelte app, and we're using Svelte 5. Of course, here Svelte 5 is the rather new version of Svelte, which came out in October 2024. And I highly recommend using Svelte 5 from the beginning if you're just starting out. And I also recommend you to switch over from Svelte 4 to Svelte 5 if you haven't done it yet, because Svelte 5 is really awesome, and it comes with so many nice features that you don't want to miss anymore once you started using Svelte 5. So this is a standard Svelte 5 app, and as it is like common in Svelte, we always have a parent component, which is this app.svelte component that you can see here. And I'm just opening this up now because this is the starting point of our application. And for now, we can just forget all these other different files that are here. Most of them are like housekeeping and setup files, config files that I haven't touched actually, that we haven't touched in our team. We're just using it as it comes from like the standard Svelte 5 installation that you can download, or if you use Svelte Kit, which is like the app framework to build larger apps that also have server-side rendering included and routing and kind of stuff, then you just have this bunch of files here that are needed to run the whole application. But for now, for our custom implementation of the Sistine Chapel smoke, we can focus on the app.svelte. And yeah, this here is the code of our parent component. And when I read foreign code, like in other projects, for example, I always start with the HTML part that we have in this case here in the middle, because that tells you something about the architecture of the application. We can see there's a wrapper div, which here in our style gets some width 100% and a height of 100 pixels. So it has like defined dimensions that are dependent on your viewport, of course. And we are measuring these width and height here directly with the bind directive, and using the HTML attributes client width and client height to get the current width and height that we then store in a width and a height JavaScript variable here. And then within that, so we have first a component which is called chimney, which might draw this little chimney here. Yeah, you're right. Actually, I haven't drawn this. This was drawn by my colleague Niklas Marienhagen. Thanks to you. Really great SVG stuff. We're looking into that in a second, how it looks like. And then we have on top of the chimney, actually, we have like this canvas here. So canvas is opening up an area where we can draw, and it gets also the width and the height again. And we have here a component which is called smoke, which probably generates the smoke. And this one takes like two properties, which is the origin, two elements array, which is just using two numbers dependent on the height of our application here for setting up the origin where the smoke comes out of the chimney. And we have the color, which is basically the color of the smoke. All right, but before we go into the smoke, so let me quickly go to chimney. And as I said to you before, it's just an SVG. So we have here an SVG where we have rectangles, where we have a polygon and stuff, and also some styling for it so that our chimney gets the right color. Actually, there could be an empty line added, so a little bit nicer like that. And yeah, this is just drawing our chimney. So probably when I maybe just put out this polygon here, you can see that basically the top part of the chimney is gone. Yeah, so how can I make this? Oh, doesn't work. Like that. All right, so we got our cool chimney back. Thanks, Niklas, again here. So this is just our SVG. And then we have the smoke, which is running here on this canvas. So canvas actually is here not the standard HTML5 canvas element, because this would be just with a small c here, but here with the capital C, indicating that this is a Svelte component. And also usually a canvas in the HTML world cannot have children like this smoke element here. This is not possible, but in the Svelte world, of course, this is possible. So smoke is a child of canvas. But let's have a look at canvas first. So let's just go into canvas. And yeah, also here, let's start with the HTML part again, which is this part here. So here now we have an original HTML5 canvas. Now you have the small c here. And this canvas gets width, height, and it also gets a style with height. This is the style directive coming also from Svelte, which means this width is written into the CSS, whereas this width here is an HTML attribute. And this is the first trick in this project, which is very common when you work with canvas. Usually canvas, when you draw on canvas, you draw pixels, and it very quickly can get very pixelated. And to avoid that, you usually define a canvas with the HTML attributes width and height with your twice the width and twice the height you are inputting from outside. So you make this canvas a lot larger than you actually need it. And then with the CSS variables, width and height, you actually define the correct width and height that you want to have. So there is a canvas with double width and double height, but you make it small to your original width and to your original height again, which increases just the resolution on this canvas. And then we're using the bind directive of Svelte again to get a JavaScript reference to this canvas that we also call canvas. So this is actually, you can see it here in line 7, just a JavaScript variable that holds the reference to this canvas element. And then we have this part here. So if a variable called regal is there, then we should render the children if they are there. And the children, this is our smoke component that we are looking into in a second, okay? So yeah, we have the canvas here. And if regal is defined, then we also render the children, which is the smoke as such. But what is regal actually? So we can see here that regal is defined as a Svelte 5 state, which means this is a reactive variable. So with the $state rune, this is a function which is coming from Svelte 5. So we can just use it here. With that, we define regal as a reactive variable. So we tell Svelte, okay, regal is a variable that might change during the runtime of our application. All right. And then on mount here, that means when the component is mounted, when the canvas is already existing, then we run this function create regal with the canvas element as an argument to this function, and that defines or redefines our regal variable. So what is regal? What is create regal? Let's see where create regal comes from. Create regal is imported from regal, and actually regal is the dependency of this project. So regal is a framework that makes it possible to use WebGL within your project in a very easy but still low level way. So WebGL is drawing on the canvas. That's what we also know from like 2D canvas stuff. But when we use WebGL, all the computations that are needed to draw on the canvas are not run on your CPU, but they are run on the graphics card, on the GPU. And GPU has a big advantage. It can run a lot of multiple calculations in parallel. And that's exactly what we need here, because for every pixel basically here on our canvas, we want to calculate a different color value later on to get that simulation of the smoke. And this could be quite heavy if you run it on the CPU, because the CPU is just calculating every pixel after each other. That might take a while, depending on how large your canvas actually is and how complex your animation is. But when we run this through the GPU via using WebGL technology, then we could highly parallelize these calculations. And using WebGL directly with JavaScript is possible, but there's a lot of boilerplate going on. You don't want to do that actually. And this is why I love using regal, which makes it a little bit easier. And therefore I have to use this create regal function, which generates my basic regal object, let's call it like that for now, that I now have to use to draw on this canvas. So if I need that to draw on the canvas, I have to pass this to components that want to draw something on my canvas, like the smoke component as well. But here there is no smoke component yet. The smoke component is like in this children here, which is the smoke component, but the smoke component is not here inside this file actually. So I need to send this regal state to other components, and this I can nicely do with context. So I can tell all the children of Canvas that there is something like regal that they can use. And I do this here in line 10 with the setContext function that I import from the Svelte library. And I call this context smoke regal. You can choose whatever you like, just need to remember it. And then I define a function here. And when you call this function, you get back the regal object, and I also send the width and the height that we're working with here, because I need that as well for some calculations of my smoke. You'll see that in a second, so I also send that. So it's important to put a function in here, because later on I call this function, then I get the current version of my regal, of my width and my height. This is the important stuff here. Otherwise, I wouldn't get this as the regal as a reactive variable. Okay, that's a canvas. And you remember, if you go back to the app.svelte, you can see the canvas. Yeah, it got the width and the height. And I used the width and the height to build up this canvas here. And I also sent the width and the height further to all the children. And then within Canvas, I have this smoke component. And yeah, you can nicely see there is the origin now as prop, as I've said to you before, which basically defines where the smoke should start. So we have an X value, which is height divided by 2 plus 5 pixels. And we have a Y value, which is height divided by 2. And if I just increase that from 5 to 50, you can already see that the smoke is just starting from a different X position now. So let's move that back. And then we have the color. Let's play around with that in a bit. The color needs to be in a hex format here, because I defined it like that. You see in a second as well. But you could put in here whichever hex value you want. Let's play around with that in the end as well a little bit. All right. So the magic of the smoke seems to be happening within the smoke component. So let's go into the smoke component, and surprise, surprise, it's only 29 lines of code long, which might surprise you a little bit. So let's see what's happening here. So Here we have some imports. Let's skip that, but let's start in line 6 and line 7. So in line 6, we can see that with the $props rune, we are getting back the origin and the color. So in case the origin is not set, it gets a default value of 0, 0. So that the origin is always a 2 elements array. And then here we pull out now the regal object, the width and the height, from our context smoke regal. And remember, it was a function, so here brackets, round brackets in the end, we need to run that function, getting back now regal width and height. And then we put all of that into a derived rune, which means, hey, regal width and height should stay reactive variables also here in this component and be dependent on their original regal width and height values or reactive variables states. And whenever width and height or regal is changing, then also here within the smoke component they will be updated. And that's quite important, because when I change the width and the height, so let's just try it here. So when I change the width, you can see that then the smoke also gets extended on the x-axis a little bit more. Okay, let's make that like that again. All right, then we have a constant n, which is 1000. This is like the number of particles that we now want to generate, because here in line 11 and the following, you can see that we generate a lot of particles actually. All right, and this is, to be honest, the point in our application where all the magic happens, because this whole smoke animation here is just a particle simulations. It's 1,000 particles that are shown at each point in time that are moving around, that have like a little blurry filter on them, that have maybe slightly different colors on them to imitate the smoke which is coming out of this chimney here. So we are creating here the particles. We use regal for that. We'll see in a second why we need the regal object here. And then I have here a whole object of different settings where n, like the number of particles, runs in, where the width, the height, the origin, and the color runs in, because this is all what we need to know to generate our particles array. So it's already, I can tell you, it's an array of particles. All right, so that's the particles. And they are also derived here again, so which means whenever regal n width, height, origin, or color, well, n is a constant, but width, height, origin, color is changing, then the particles are recalculated. And with the inspect rune, we can have a look into the particles object now. So if I start it, you can see, oh, here it's a regal buffer, and this looks really weird. Okay. A regal buffer, what's that? I think we have to go into the create particles function in a bit to see what's really happening in there and what particles really is. But just to continue here, let's assume we now have the definition of 1,000 different particles that are moving around here. We then in line 15 here generate a draw particles function with the create draw function call, and with regal as an argument again as derived, because regal could change when the application is running up. And then we have a function which is called draw particles that can then be used to draw these particles. And then within this effect rune, which means, hey, whenever something here inside changes, then you have to do another setup of this function which is in the effect here. Within that, we have basically this regal.frame function, which is a little bit similar to request animation frame from JavaScript. If you know that, this is used to run a function again and again whenever the browser basically has time to draw again. And we get here as one of the arguments that go into this inner function, the tick, which is like the number of frame. So if I do just a console.log tick here, you can see on the right hand side that we are running 19,200 something round of this. And if I do a restart here, it starts at 1 again. So whenever a new number here on the right pops up, we have a new frame which is drawn to our canvas. And this is quite quick because it's happening on the GPU. And then the first thing you do is a regal clear, which means, hey, erase everything which is on the canvas. And then we do execute the draw particles function, which gets n, again, the number of particles. It gets the particles buffer, whatever that is, and it also gets the tick. We are looking into that later, what draw particles is really doing. Whenever this is aborted, then we run tick.cancel, which erases everything in our memory, which has to do with this request animation frame here. All right, let's go back to the particles. So what's really happening here? And before that, just to make it a little bit clearer to you, I just do only 100 particles, then you can see, okay, now it's only very few dots. And if I go to 10 particles, you can see, okay, now it's only really 10 little blurry circles that are running out of the chimney here. So let's go back to 1,000. Actually, what's happening when I use 10,000? Oh my God. Well, this doesn't look very natural. So let's stay with 1,000 particles. So the n,000 particle goes into this create particle function. And I open that, I stored this in a utils.js. You can see it also here in my file browser on the left-hand side. It's in the same folder as my smoke component. And okay, here's a lot going on. There's a lot of functions. A lot of that is helper functions. But let's go to the create particles function here. It gets the regal, it gets then all these different settings that we put in. And this function basically consists of two parts, and in these lines it's really the magic happening. So we are generating here a particles array. So this is an array with the length n, so 1,000. And then, oops, these hovers are, well, nice. So here we get, for each of the particles, we get like these properties. So we get an object for each of the particles, and each of these objects has a position, a velocity, a size, a color, opacity, and a life. So this is what particles need. So basically they need a position, and you can see that they are getting positioned to the origin in the very beginning. And the origin then is recalculated from the pixel space into the WebGL space, because in WebGL our coordinates run from -1 to +1, and same on the y-axis. So we need to transform that with the width and the height again, and this function to WebGL coordinates is doing that. So we're getting here a two-membered array back with the correct position of our origin in the WebGL world. Then we get a velocity. This is basically the velocity these particles are moving when they are running around. And this is again a two-membered array. This is like the x velocity, and this is the y velocity. And you can see here now that with math random, this is a different value for each of the 1,000 particles. So with math random, we take a random value between 0 and 1. Multiply it with 0.6 and again with 3. So I tried a lot of different values here. That's why it looks a little bit weird. Of course, you can also multiply with 1.8. And so we have like here a positive x velocity. This is why everything runs to the right. And then we have here a y velocity with which is math random minus 0.05. So that means we get here a random value between minus 0.5 and plus 0.5. times 2, so that means that some particles run a little bit to the top, some particles run a little bit to the bottom, and some just stay in between there, which makes like this little angle, plus minus angle that you have with the smoke. Then we have a size, which is the size of the particle. Also there we have a random value, which is in between some specific minimum and maximum values. That's why this is looking a little bit complicated, and it is dependent on the height. So the more height we have, the larger the smoke basically gets. And then we have the color, of course. So we take the color that we want to have. In that case, it was black. And then I'm running this shade function here. So if you're interested in that, this is here in the color. I took that from Stack Overflow. You could also use Chroma.js, for example, to achieve that. So, but for like, if you only want to change the color a little bit, you could just use these functions here. So So you put in the color, and then here with math random minus 0.5, we get again a value between minus 0.5 plus 0.5, which makes the color a little bit darker or lighter depending on our random variable, which is making like this little organic effect that the smoke is not all black, but there's also a little lighter smoke particles in between. And then again, we have a hex color in a hex format. We cannot use that in WebGL. We need to transform this into WebGL color, which is RGB. And RGB values of R, G, and B between 0 and 1. So for example, black would be 0, 0, 0. In WebGL colors, I also have a little function here, which is doing that, giving us a 3-member array of color. Then we have the opacity. So yeah, just the opacity. Here I just use a random value. And then we have the life. This is how long these particles should exist. Basically how far they get away from the chimney until they die. This should be also a little bit different to get like, this is how smoke works actually. There is a lot of smoke in the beginning and then it gets less and less. And this, I don't do it with math random because there you get a uniform distribution of values between 0 and 1. Here I want, like most of the particles have a life of 0.8. And I use then a Gaussian distribution, which you generate with a random normal function from D3 with a standard deviation of 0.05. So we get a lot of particles at 0.8 and a few particles that have more or less of 0.8 life. And yeah, this is a little trick to achieve that. I mean, you can play here with the standard deviation and then you see that, for example, your smoke gets more scattered. Yeah, I found that 0.05 looks quite nice. All right, and now we can do another console log and just have a look into this particles variable. And then indeed we can see here is an array with 1,000 values. And if we go into this, we can see, well, there's a color here 0, 0, 0, which is basically now the black color. Then we have a life of 0.83 something. We have an opacity, which is quite low here. We have a position. This is our 2-member array in WebGL coordinates. And we have the size of the particle. And we have the velocity, which is here certainly positive for x because it's always positive for x, and here a little bit negative for y. So this is a particle which is basically moving upwards because, or is it down? No, it's downwards actually. All right. So this is one of the particles, and then I have 1,000 different particles here as well. All right. This is nice. This is readable. Let's get rid of that here. But then I want to change this into a particle buffer because such an array with JavaScript objects is not readable for our GPU, for our graphics card. So I need to put that in a regal buffer. And for that, just take the particles and map them into an array where I put all these different values next to each other. So I first have position x, position y, velocity x, velocity y, the opacity. Then I put the 3 color values R, G, B in here, the size and the life. And after that, that's why I need regal here, I put that into this buffer method that creates a particle buffer that I return. And this is exactly, going back to smoke, this is exactly what particles is. And particles is then used in the draw particles function to be drawn. So now I have these 1,000 particles. I need to draw them. And optimally in each frame of that animation here, which is running again and again, it's a loop, I need to move the particles a little bit by their velocity. And the information, how far we already got, is in this tick variable here, because this is telling me how far I went in my animation already. Okay, I'm ready to look into this because we haven't done any WebGL yet. So now it's the time to draw. And for that, we need to have a look how this draw particles function looks like. So let's do a constant, no, let's do an inspect because this is a reactive variable. And we look into this draw particle function, we can see, hey, this is a so-called regal command. Oh, I should have clicked on that. Sorry. This is a regal command, and it looks very cryptic, so we cannot learn a lot from that. So it might be easier, let's get rid of that again. It might be a lot easier to look in this create draw function, which is also in utils. And where is it? Ah, here. This is the create draw function. This is creating this regal command, draw particles, that we are using. We're using like here regal again, and we can call regal, and we can put a very large object into regal that is creating us this draw function, and which holds all the information to draw stuff on the GPU. First property is vert, second property is frag, and I hope that you don't switch off now because it gets very cryptic. I'm trying to explain how it works. So vert and frag is basically just text. This is the two shaders that you need. This is the little programs that we send on our GPU to draw the particles. With the Vertex shader, we basically, I simplify now, we basically draw the coordinates of our circles, and with the fragment shader, we tell the GPU how these circles, how these particles should look like. Okay, then we have attributes, we have uniforms, we have some settings here, depth and blend, we have a count, and we have primitive points. Okay, let's start from the bottom. So with primitive points, we are telling the GPU we just want to draw points, circles. With count, we're telling the GPU the number of circles, of points that we want to draw. And we tell this here with a little function. So this function only works because this is an object within the regal variable, within the regal function call. And here as the second argument, we always get the properties, and these properties is exactly what we put into our later draw function, where we had n ticks and the particles, and with props.n we can then say, okay, yeah, this is the number of particles here. Actually, we also have particles in general here, I think, particles, which is also like this, this buffer. And if this would have been an array, we could do something like that. Now we can't do that because it's not an array anymore, because it's this buffer, so we have to use n here. All right, blend depth. This is just some settings that we need to get transparencies right. Maybe I could just switch that off and then we can see what's happening. Nothing, because like this transparency that we have, a transparent background where we have blurry half transparent circles on it, this is only possible with these settings. I won't go into a lot of detail here. This is like some rules how to add or subtract different colors from each other. And with blend enable true, you say, hey, this needs to be transparent. All right. Then we have uniforms. So uniforms are variables, like here, time and wind, that are true in the same way for all of our 1,000 particles. So all of our 1,000 particles, you can imagine, are now calculated and drawn on different parts of our GPU. This is the parallelization. We can run this 1,000 different particle calculations in parallel, and uniforms are like spread out to all these 1,000 and used by all these 1,000. So the time, for example, is basically how far we are in the animation. So here you can see we're using tick. I multiply this by 0.001 because I want to move very slowly through my animation. I can make this a little bit larger, and then you can see, oh wow, now it gets very fast. And the 10 plus I do because I want to start right in the beginning in the middle of my animation. So here you can see, well, the smoke is now firstly coming out of this whole thing. It doesn't look very nice. It looks asynchronous. This is because we have these small tick values in between. We see that later why this is an effect, and with the increasing this by 10 or shifting everything by 10, we can get rid of that. Don't ask me how long I needed to find this out, but yeah, you see in the shader later why this is important. Okay, and then this is uniforms, and then on the opposite of different variables that we also have attributes. And here we have the position, the velocity, the opacity, the color, the size, and the life of our particles. And of course, these values are not the same for all of the particles, unlike time or wind. I talked about that. Let's do that later. But these variables here are different for all of the particles, and this is why we call them attributes. And let's go for the position first. So all this information is, you remember, in this particles buffer. Okay, how do we get this out there? So basically each particle now has an array where all of these values are stacked together, where like there's the position with 2 values, then there's the velocity with 2 values, and what else we have, like color and opacity and all that kind of stuff. So here we say, well, position is coming from a buffer. And then we use here with this function, we use the buffer props.particles because that's where we put the buffer in. And then we say we are reading now values here with an offset of 0 because the position is just the beginning. Remember, x and y value, we put those first into our array for each particle. And with the stride, we define like a step from in this very large array. You can imagine that we have, we have 10 different values per particle. We have an x and y position, we have an x and y velocity, we have 1 value opacity, we have 1 value size, we have 1 value for life, and we have 3 values for color. Yeah, this is 10 values that we have per particle. And in the buffer, each particle is coming after each other. That means we have 10 values particle 1, then 10 values particle 2. Each value has a size of 4 bytes. And this is why the step we need to read out the particles is 40, because 4 bytes times 10 variables that we have. So every 10 variables we have repeating the same property of a particle. So every 10 values is the x position, every 10 values is the y position, and so on. This is what we're defining here. So we read from 0 and we need to step by 40 bytes. All right, then we have the velocity, and the velocity, again, stride 40, this is again the step. This is similar for all of them because our particles always have the same size of properties. So yeah, this is 40 all the time, but now the offset is different because the velocity is now not in the first byte, not in the second byte because that was the position, but in the third byte. So after 8 bytes, we start with byte number 9, and there we have the velocity in. All right. The velocity is again 2 values. That means the opacity then needs to be read with an offset of 16 bytes. The opacity has 4 bytes, so the color needs to be read from with an offset of 20 bytes. The color now is 3 values. 3 times 4 bytes is 12, so 20 plus 12 is 32. That means the next value size is read with an offset of 32, and the life is then read with an offset of 36. And this is how the graphics card is getting out the information from a very large array, from a 10 value times 1,000 particles, or from a 10,000 member array, which is in this buffer basically, getting out all this information. This is just an effective storage of a lot of values for a lot of particles in a readable format for our graphics card. All right. So now you can imagine, well, there is now these 1,000 particles are calculated in 1,000 different little kernels on our GPU, which is probably not the accurate term that I'm using now, but no matter. Let me switch off my light at this point here. It's getting dark. So each of these 1,000 different little kernels on my GPU are getting now different attributes, are getting their different size, life, color, and so on that they need to calculate with. All right. Talking of the uniforms instead, the time is similar, is the same for each of these 1,000 calculations. And then there's another thing which is like the wind. So wind is an additional velocity they put on all of these particles on top of their dedicated velocity. It has no x value, so the wind has no x component, but the wind has a y component, and I use here the sinus of the ticks time 0.005 to make the smoke run a little bit to the top and to the bottom in this like pendulum way. I can show you that when I make this here a little bit larger. You can see that this is now going to the top and then slowly going down when ticks are increasing and then going up again. Just very slightly. Let's go back to 0.3. All right, that's everything we have set up. So now we can tell our GPU how it should do these things. All right. Now we need to have a look at the two programs that are running on the GPU, the Vertex shader and the fragment shader. And this word frag stuff is just text. I told you before, it's just a string for each of them. I import them here from word.glsl and frag.glsl, and with this question mark raw, you just get the text back from these files and you can just import them. This is really nice actually. Let's go into Word before, oh, you can't click on that. I need to open it here via the file browser. So this is my Vertex shader, and you can already see this is not JavaScript anymore. This is now GLSL, so this is our WebGL language, which is like a little bit C-like. And you can see that there is a general definition here, which means what is the precision of calculations that we're doing. This is now medium P, it could also be high P. And then we have now our different attributes here. And you can see we define first the variables with the variable type, which is an attribute, so the WebGL type. And then here we have the variable type, which is a vector with two members. So basically an array with two members, position and velocity. We have a float for the size. We have a vec3 for the color because we have the three RGB values. We have the float for opacity, float for life. And we look at the uniforms here in a similar way, the time and the wind. And then we have these varying variables. These are variables that we do newly define here in the Vertex shader. I tell you what we need them for in a bit. And then we basically have one function, void main. So this is the main function with the return value of void, which is nothing basically. And everything which is in here is running again and again when we have a new frame and a new frame. Okay, let's go through this. And you remember the Vertex shader is predominantly there to define the position of our particle. And the first thing is here we calculate an age. So we have the time, which is basically the frame where we are in, and we have the life. This was a random value around 0.8. And what we do here with the mod, which is the modulo function, we're getting back a value between 0 and 1. Basically how old this particle already is at a given point in time, and if it still lives or not. And then we calculate a new vec2, so a vector with two members that we call new position. And for that we take the current position, which is the origin in the beginning, then we add the velocity times h, and we add the wind times h. So this is calculating the position of a particle after a given time, after a given age basically, which is normalized time here of this particle. So this is already at the new position of our particle here. Then we have these three varying, and varying variables are quite interesting because these variables can be used to transfer information from the Vertex shader that we're in here to the fragment shader, which is doing the actual drawing color stuff. And what we do here, we transfer the remaining life, which is 1 minus h divided by life. So it's a value between 0 and 1. Then we just take the color here and put it in varying color, and we take the opacity and put it in the varying opacity, so that we can just pass the color and the opacity further into the fragment shader. Okay, let's store that in our memory. What we also do is we calculate this float size factor here, which is basically the sinus of the age. So that makes my particle to get a growing size and a shrinking size depending a little bit on the age. And then we have this GL point size, GL position. This is basically global variables of that vertex shader that we can just use. This is defining now the size of my particle here. And this is basically taking the size that I get from my attribute here, multiplying it by the size factor. And it should take maximum the size that I defined. This is doing this max function. And then I also set the position. The position always needs to be a vec4 with these 2 1s here in the end. So I have my new position, which is in vec2 first, where the x and y is. And I add 1 1, and then my vertex shader knows where to draw this particle. Okay, this is just now size and position. We now need to draw actually, and we have set like these 3 variants, and they are now passed into the fragment shader, which is looking like that. And you can see here the precision is on high P float Z. And then we have these 3 variants, the remaining life, which is a float. We have the color, which is a vec3. And we have the opacity, which is a float again. And now with these 3 lines of code, we're doing like these blurry particles now. And it's really surprising. Also, it was surprising for me when I coded that it's so easy to draw it actually. So, well, what we need to do is we need to define this float dist variable, which is actually using here the GL point coord, which is the current position where my particle will be drawn. And I'm subtracting here this vec2 of 0.5. So this is a vector 0.5, 0.5. And then I apply this length, which is giving me the length of a vector, which is basically telling me something about how far am I on my current pixel that I'm looking like away from the center of my point coordinate. So you can imagine that each point is, as you see on the screen, are not just one pixel, but each point that we're drawing here is consisting of multiple pixels, and the fragment shader runs through all of these pixels that belong to the point. And here I can get an information about how far am I away now from the center of my point. And this then is used in this calculation here to generate an alpha, that means an opacity, for that certain pixel. And with smooth step, I use that distance to apply a value of between 0.6 and 0.02. So I transform the distance onto this range. And then I multiply this with the remaining life and with my set initial opacity value, and this gives me an alpha for a certain pixel which is within my point. And then I use that alpha multiplied with the color so that I get this vec4 here. Again, there's space too much, and this is giving me the color. Okay, this is quite, it's just 3 lines, but it can look quite complex, so let's play around with that a little bit. So for example, I use that distance here to calculate alpha values between 0.6 and 0. So if I say, okay, this should always be between 0.6 and 0.5, you can see a little bit more what I mean now. Because now we are not getting like these blurry circles anymore, but now we are getting like the full circles, which is also rectangles in a way, that are drawn then, because whatever the distance is, I always try to set the value between 0.6 and 0.5, all right? So if I make this to 0 again, it works. If we go the other way around, 0.1 to 0.0, you can see, well, then only in the very inner, so the pixels that are very close to the center of my point are then drawn, and then we can see the particles quite nicely, how they flow out of the chimney and how they get all these different positions. So yeah, I want to make them a little bit larger. 0.6 proved to be a nice number, because when I make this to 1, then yeah, I get this rectangle shape again, because the points in WebGL are actually rectangles and not circles. 0.6. All right, and then I multiply this with the remaining life, meaning that The older my particles are, the less visible they should be, and then I multiply it with the random opacity value. So I can also take that out, and then you can see they are more uniform. And with this V opacity, which is a random variable for each of the particles, remember, I get a little bit more variety into that. That's basically it, how this whole stuff is drawn. And as this color here is originally coming from this hex value, we can really tweak the color here in our parent app.svelte component. So for the white smoke, for example, we can use the 6Fs for the hex code of white. And of course, everything in between is possible. So one of my favorites, for example, is this purple smoke. And as we are in Svelte, of course, we can also do things like putting that whole div into and each block. So, and then we can define different chimneys, different skies with different colors. So we can start maybe again with the black, and then we have this color variable, and we can, instead of using a fixed color here, we can just put it in and we get this black. Again, if we want to have the purple, we could just add that here. And then we get a second one like that. And of course, we can do whatever we like. We could also say, let's do a yellow one, or a solely green one, which should be doing that. Yeah. So yeah, this is basically how this works. And yeah, it looks maybe simple in the beginning, but WebGL is a little bit hard to understand, especially when you see it for the first time. So I just encourage you to go to the Spiegel Graphics GitHub, where we have open sourced this whole project, which is just called Smoke. And just check it out, clone it, and change values, add stuff. I'm curious to see what you're doing, basically. You find the link to the repository in the comments or in the description of the video. And yeah, have fun and use WebGL for whatever you like. It's especially cool for calculations that can be parallelized a lot, like these smoke particles. That's it. So thank you for being with me. It is now quite dark here in Germany because this took longer than I thought, but hopefully you learned something. See you next time. Bye.